I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for these students and for this class. Just ask you to bless our work today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So today I am introducing one of the last best important concepts for this course. Really one of two, maybe, important calculational problems that we have left. The two problems that I have in mind would be the line integral and the surface integral. Today we're going to at least define the line integral. All right, so so it's called the line integral, but that's a bit of a misnomer because it's really an integral along a curve, and the curve doesn't have to be a line, but oftentimes this is called the line integral, at least in the circles I'm from. So here's the definition. Let gamma be a parameterization of a curve, C, all right, be a differentiable path which covers the oriented curve. All right, the oriented curve C, and suppose that the domain, that C is a subset of the domain of a vector field F. All right, for a continuous, excuse me, continuous vector field F. On R3, then the vector line integral or as I'll often just call it, the line integral of F along C all right, is denoted and defined as follows. And here it is. Let me get a better marker. The integral along C of F dot dr is equal to the integral from A to B of F of gamma of t, all right, dotted with the gamma dt dt. As I've indicated in our discussion leading up to this, this calculates the work of the vector field done along the curve, if you want to think about it in terms of physics, or it calculates the circulation of the vector field along the curve if you want to think about this idea in terms of like fluid dynamics. But who thinks in terms of fluid dynamics, honestly? I don't know. Or like, well, who thinks in terms of physics? Well, I guess I do. But fair enough, you got me. If you ask me, is this the area under some curve? Like this was drilled into your head in Calculus 1. An integral is an area under a curve. Well, yeah, except when it's not. Like, which is almost always. In anything except for Calculus 1. It's very rarely, the integral is very rarely the area under some curve. It is always a continuous sum. And this is adding up something about, like look what you're adding up, right? What are you summing? You're summing a vector field evaluated along the path, right? So if I drew a picture to try to illustrate what's going on here, if this is the point, well, this is the curve rather, right? And so it's initially at gamma of A, and it's terminating at gamma of B. So this is a curve. It goes from there to there, okay? It's an oriented curve. It has a beginning, it has an end. This is important. And the vector field is independent of the curve, all right? So like, for example, the vector field could, who knows what the vector field looks like, but if it looks like, let's say this, all right, and then it kind of bends over like that, all right? What's going to happen with this vector field as pictured? Let me describe it. So, right from here, basically from here to here, right? Along this part, we'd have the vector field evaluated at the path, right? Dotted with, what is this d gamma dt, by the way? What is this? It's not the speed, but your heart is in the right place. But you need to give your heart a direction. Velocity, yes. So I'm sorry, that was horrible. But yes, this is the velocity. So that is the tangential, that's the tangent field, right? It's almost the tangent field. It would be the tangent field, but we usually talk about the unit tangent, so it's not quite the unit tangent. We could rewrite this in terms of the unit tangent, couldn't we? We'll do that in just a second here. But this, see, we have, this is equal to what? For my first part, I'm trying to draw it so like from here to here, it is perpendicular, right? Which would mean that the line integral for that part, all right, the line integral for that part there would be 0, right? Because here's your, let me say that's t, right? Remember that unit tangent we talked about before? In fact, how could I rewrite this formula in terms of the unit tangent? What would I do? You guys tell me how I would rewrite the formula in terms of the unit tangent. What was the definition of big T? You guys remember? You're like, but we're past that. We don't have to talk about that anymore. That's in the past. It's also in your future. So let's talk about it. So d gamma dt divided by what? The length of d gamma dt. That is the unit tangent, right? So if I take the formula I have, I can rewrite it as the integral from a to b of f of gamma of t, right? Dotted with what? d gamma dt. Man, I'm really tired of it. I'm going to use the prime notation if you guys don't mind. Gamma prime of t divided by the length of gamma prime of t times what? Times, well, gamma prime of t. Now what does this assume? I am assuming that the parameterization's non-stop, right? If the parameterization stopped, then, well, that would be bad, because then the speed would be 0 and I'd have division by 0, which is, ideally not what we want to do. But with this simple division and multiplication by the non-zero speed, well, look what you got. See this right here? This is the unit tangent, right? And so, and this right here is what? Remember this? This is arc length. This is ds, right? And what you're really looking at now is the integral along the curve of f dot the unit tangent integrated over arc length. In terms of the arc length integral we had defined earlier in the course. Remember? We talked about how to integrate along a curve with respect to arc length. That's something we defined previously. We didn't spend a lot of time on it, but we did introduce the concept, right? When we calculated arc length and such. So another way to understand this line integral is we're adding up the part of the vector field which is parallel to the curve in question. See that? And so along this part, the line integral would give me 0. But then as the vector field bends into the direction of the unit tangent, the net result of the line integral along my pictured curve would be positive, because at the end, the vector field's aligning with the curve. All right? Special case. If the vector field was always perpendicular to the path, we should get a line integral of 0. Let's work some examples. So let me see if I can find you one that's going to be 0. How about this? F of x comma y equal to, let's say, x squared y squared. That's interesting enough. And let's let our curve be x comma y such that x squared plus y squared equals to r squared. Could you guys tell me what that is? Now, you're like, wait, hold on a second. One thing you haven't emphasized enough yet, well, that's kind of my problem. That's not really your problem. That's kind of my problem. One thing I haven't emphasized enough yet is the fact that C has to be an oriented curve. So until I tell you the orientation of C, my example 1 is ambiguous. So let's say that C is oriented in the counterclockwise fashion. All right? And if you're really paying attention, you might complain that my example 1 is outside the scope of my definition, right? Why is that? I wrote the definition, what? As if we only take line integrals in 3 dimensions. But is that the case? No. This definition really makes sense in n dimensions. All right? So I don't know why I put R3 in the notes. It really doesn't have to be R3, right? You just, the only place 3 dimensions figures into any of this is here, right? You can take this 3, cross it out, and do what? Put n here. It's just the same. Because we can take the dot product in n dimensions, and we can calculate, everything I wrote there is possible in n dimensions. Now, you got to watch out. If we start writing stuff about cross products, then that's an intrinsically 3-dimensional thing. But we didn't. So let's calculate the line integral of that vector field along the circle. Let's see what happens. All right, here we go. So well, wait a minute. How do I do that, though? What do I have to have in order to do this? You have to have a parameterization. That's right. So we have to know the parameterization of the curve in order to take the line integral. So the parameterization of this, the nice one, I would say is this: x equals r cos t, y equals r sine t, 0 less than or equal to t less than or equal to 2 pi. Okay, that's what we're going to do here. So we have integral from 0 to 2 pi of f of, I'll write it symbolically here for a second, f of r cos t, r sine t, dotted with d dt of the parameterization, which is r cos t, r sine t, all of that, dt. Now the last formula I wrote on the left board, the one about the dot product of the unit tangent, that's of theoretical use, but it's not usually of calculational use. In other words, I don't actually want to calculate the unit tangent to calculate the line integral, right? That was more of a trying to explain, what it is conceptually. That's why I did that calculation. For the most part, we don't have the unit tangent without a bunch of calculation, right? So you guys, what do I have there then? What am I up against here? I'm up against the integral from 0 to 2 pi. This vector field is r squared cosine squared t, r squared sine squared t. And I'm taking the dot product with the velocity, which is minus r sine t, r cos t. And we integrate. So what's that equal to? Looks like we've got a minus r cubed cosine squared t sine t plus r cubed sine squared t cosine t let's see here. So we can make a substitution, right, to do this integral. Like here, think about u equals cos t, and over here you can think about a w equal to sine t, right? And so we've got something like, you know, r cubed out front, and the integral of this guy is, you know, 1/3 cosine cubed t, I believe. And then over here you've got plus 1/3 sine cubed t, as it happens. And that all gets evaluated from 0 to 2 pi. Interesting. I wanted the dot product of the it should have been 0. Something feels wrong here, guys. Well, that is 0, but I felt like the f dot v should have been 0. By the way, for those of you who care about physics, remember this right here, in terms of physics, is the force dot the velocity. Right? That's the force dot the velocity, and that is, what is that? Do you guys remember, if you've had physics, what is force dot velocity? Nope. Nope. Force dot velocity is power. In other words, it's the energy per unit time expended by F. So what you're doing here is you're integrating the energy per time, and that gives you the net energy that is expended by F. In other words, the work done by F, if you want the complete circle of ideas in physics. But anyway, and you know, as I try to keep mentioning, while physics does motivate these things, it is not necessary for the calculation thereof. Okay, so I'm just a bit bothered. I wanted this. I thought this should be 0 at right here. This should be 0. Unless I'm misunderstanding. I must be misunderstanding something here. Yeah?
Is r negative r sine t squared? Is r squared in that or not?
What are you asking here?
Oh, no, wait. Is the second part of the line integral on the first step? Yes.
Well, yeah?
I don't understand why you have r squared cosine squared. Like, how did you get to the square?
Oh, so that's because f of x comma y is x squared y squared. So since x is our cosine t, I put it there, and that goes there. The thing that's bugging me, guys, is it should have been 0. Like, there's something wrong idea in my mind. I'm not sure what it is, guys. Because if you look at the unit circle, right? And it's counterclockwise. It doesn't really matter so much, but it's counterclockwise oriented. So it goes like this, right? That's my C. What's the direction of f of x, y here? Notice that it can be written, oh, that's where I'm wrong. I was thinking that this has the same direction as this guy. That ain't the case. That's not the case, right? Does this have the same direction? Is this parallel to x squared, y squared? No. That's my error in my mind. The reason that's an error is because, of course, x squared, y squared is always pointing which direction? Positive, right? The angles that can take in terms of standard angle are between 0 and pi over 2. So no matter where you are in the unit circle, that thing is always pointing somewhere up in there, all right? That's my actual f. But nevertheless, what's the integral around the circle? It works out to 0, doesn't it? See that? And why is that? Well, it's a little bit more complicated than I was hoping for, but essentially the story has to be something like, for this particular vector field, like how does it start out? At 1, 0, it's just like this, right? And at 0, 1, it's like that, right? And down here, it's also like that, right? And over here, it's also like that, right? And it's something like this here, and it's something like this here, right? And it's something like this here, and it's something like this here. It's always pointing that away. But the tangent to the circle, which direction is it pointing? Well, that varies, doesn't it? So like the tangent to the circle is right here, 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 right? So the way that the vector field lines up with the tangent, there's a symmetry to it, right? And it's giving you positive work, like, I guess in certain sectors, probably, so I guess the lower half of the, it seems like the lower half of the circle, the vector field at least partly pointing in the direction of the tangent, right? But on the upper hemisphere, the upper half of the circle, it's pointing in the opposite. It's there's a part of the vector field which is the opposite direction to the tangent. So I think what we're going to see is we've got negative work from the upper half circle. We've got positive work from the lower half circle, but by the symmetry, they cancel out and they're 0. Now to test my hypothesis more fully, what can we do? How can we calculate the work over the upper half circle? What do we do? Right, so to get the C+, we just, let 0 less than or equal to t less than or equal to pi. And that would give me the integral over C+ is what? We've already done the work, right? Sorry. That was unintentional. But if you take this and you evaluate from 0 to pi, what do you get? Sine of pi is 0. Cosine of pi is? Negative 1. So we get minus r cubed over 3, right? On the other hand, if we let C minus, the lower half of the circle, that would give us pi less than or equal to t less than or equal to 2 pi. It was what we could do. I mean, you could also, well, there are other choices, but I would do pi to 2 pi just for the sake of...
Wouldn't you have another r cubed over 3 because of 0 though?
Oh. Yes, thank you, Shane. Yeah, I should have a 2 there. At some point, that'll catch up with me. Now here, pi to 2 pi, it's actually what? It's the same story, except what? Now the pi is the upper limit, so we have wait a second. Yeah, that's fine. From pi to 2 pi, I have to do the evaluation from pi to 2 pi. So my 2 pi is, I get my r cubed over 3 minus the pi term, which would be minus a minus r cubed over 3. So we get 2r cubed over 3 for the work done for the line integral over the lower half circle there. And as I was explaining, you have positive work on the lower half because the vector field aligns with the circle partly, and you have negative work on the top because the vector field is in the opposite direction to the circle. Not in total, but there's a component, right? The component of the vector field, which is perpendicular to the tangent, doesn't do work at all. That's just irrelevant, right? So there's a lot to see in this example. I mean, maybe this example is too complicated. Well, I mean, it's not too complicated, but I would like a simpler example. Here's a simple one. What if I have the vector field equal to just the constant vector field ABC, all right? And my curve is, line segment from P to Q, right? Calculate the work done. So the integral of c of f dot dr, how'd that go? So in order to calculate the line integral, what must we do? What must we do? We have to do what? Well, at least at the moment, until we learn other tricks and techniques, we need a parameterization of the curve, right? How do you parameterize a line segment? Remember our trick? We do p plus t times q minus p, right? That gives me gamma of 0 is p, and it gives me gamma of 1 is q, right? So we use 0 to 1 for our parameter, here. And so the line integral from 0 to 1. And what happens with the constant vector field when you evaluate it on the curve? How do you evaluate a constant vector field on the curve? I would say it's almost impossible to mess this up, right? So it's just ABC. Okay, so there's nothing to do, right? It's kind of like evaluate the constant function 3 at x equals to pi. Like, it's 3. I evaluate the constant function at 42. It's still equal to 3. You know, I mean, like, it is what it is. And then the dot product with the velocity, what's d gamma dt? In this case, it's q minus p, right? But notice in this problem, this right here is just a number. That's a number, not a hashtag, to be clear. All right? No hashtags in my class. I insist. Let's see here. And then that gives us ABC dot q minus p times the integral from 0 to 1 of dt, which is just what? Just 1, right? Yeah. So what's the answer? The answer is ABC dot q minus p. Or if you want this in terms of physics lingo, it's the constant vector f naught dotted with the displacement r. See, if you're starting at p and you're going to q, that motion, your displacement r, is your final point minus your initial point. So the work is the force dot the displacement. This is like the intermediate understanding of work, right? In middle school, you should learn that work is like force times distance, right? That assumes what? Two things, that the force is constant and that the force is in the same direction as the displacement, right? And then once you get a little bit older, you should learn that the direction matters. So you have to do the dot product of the force with the displacement. Because if the force is applied perpendicularly, it doesn't do work, right? So of course, our concept of the line integral is going to reproduce these more basic concepts of work in this special case. But the cool thing is, now our line integral allows for the force to be variable, both in direction and at different points. So this is the full deal. All right, let's go on here, see if I can find another one. Let me do an example which is kind of, well, let me do an example related to the quiz. Yeah? Let's see, so one of the vector fields we had on the quiz, if I remember right, had an x squared and a y squared in it, didn't it? Well, let's see, what was that one? Problem 4. I had minus y squared 0 x squared, all right? So let's try to calculate a work having to do with this one. Let's try to calculate the line integral of this along some curve. Let's see here. I will consider C parametrized by x equal to r cosine t y equal to 10, z equal to r sine t. For 0 less than or equal to t less than or equal to 2 pi. All right? So one of the things I should mention to you guys, well, fine, I'll stick with it. There's another calculational notation that people like to use for the line integral I should mention at some time fairly soon, but I'll stick with my definition to start with here. So 0 to 2 pi, integral over this of the curve of f dot dr. So what do we got? We've got integral from 0 to 2 pi of, and how does it go? I have to evaluate the vector field, right? I have to evaluate the vector field along the path. So I put y equals to 10 into the formula. So this gives me what? Minus 100? Right? Minus 100. 0 is 0. And then what's my x squared? Well, x, the parameterization here is r cosine t, right? So I put a r squared cosine squared t like that. And then I'm supposed to take the dot product with the velocity of the parameterization, which is what here? Derivative of x is minus r sine t. The derivative of 10 is 0. The derivative of r sine t is r cosine t. And then we integrate. So what are we up against here? Integral from 0 to 2 pi of minus, oh rather, minus minus is a plus, right? So 100 r sine t, plus r cubed cosine cubed t dt. All right. Now, there are different ways to go around here. Like, I think at some point or another, we probably should like work out an identity for cosine cubed, which shows it's a sum of cosines, right? Do you guys know? I mean, we can do the integration. It's going to be what? Actually, I'm not sure what it's going to be. Well, this where integrates to 0. What's this integrate to? Fine. Guess you guys can make me do everything here. Cosine cubed t dt is the integral of 1 minus sine squared t cos t dt, which is the integral of 1 minus u squared du, which gives me a u minus 1/3 u cubed plus constant, where my u, of course, was sine. So in view of that, when I go over here and I evaluate from 0 to 2 pi, we get 0. Interesting. It's useful. It's useful. So in problem 4, I just want to make a kind of just plant a stake a flag here for us for future reference. Okay, so problem 4.
Why would the integral of 100 r sine t be 0 there?
Because you're integrating from 0 to 2 pi.
But then that goes to cosine.
Yeah, but sine of t goes for the full cycle, 0 to 2 pi. It has to integrate to 0. Yeah, that's how I think about it. But the cosine, it's because you've got cosine of 0, got cosine of 2 pi minus cosine of 0, which is 1 minus 1, which is, yeah. Yeah, so they both integrate to 0 because they're both, in both cases where the integral ends up with just sines or cosines, which when you evaluate over full cycle is 0. Problem 4 had what? I asked if you could have the gradient of f equal to, what was it? This, right? Yeah? That was the question. Is it possible? Actually, the problem wasn't was it possible. The problem was to, show there does not exist any such f, right? That was the problem. And so what I've just showed is that there is an integral, there's a vector field like this, right? That integrates around a circle to give me 0. Just saying, it's possible for this to happen. It's possible for, so this, in the language I'll talk about more tomorrow, the vector field, G equal to minus y squared 0x squared is not conservative. All right, it's not conservative, and yet this example shows that this non-conservative vector field nevertheless integrates around a circle to give 0. That can happen. All right. The theorem we're going to learn is that if you have a conservative vector field, it is impossible for it to integrate around a circle to give non-zero. All right? Yeah.
Are there other circles around which this would integrate to non-zero?
Probably. I mean, certainly. Now you ask me, what circle is that? Well, I don't know. I was trying to come up with one here and it blew up on me, right? So it's just, let me go with an example which I know is going to work. We're going to go badly. Well, not badly for us, but it's going to work out a different way. And so here we could look at 1 over the square root of x squared plus y squared times minus y comma x, right? And by the way, I need to introduce a notation just for the sake of, there's like another, there's a couple of popular notations. So, remark, this is not really this is not this example per se, but worth mentioning. I should have made the remark before the example, but I'm sorry, my bad. If we have f is equal to, say, p comma q, right, then the integral of f dot dr is, we can also think of it like this. This is really the integral of what? Of p comma q dot what? Well, dx dt, dy dt, dt, right? And we're integrating, say, from a to b, yeah? But if you multiply that out, you've got integral from a to b of p dx dt, dt, plus the integral from a to b of q dy dt, dt. So it's commonplace, it's a custom of Calculus 3 courses, and certainly Stewart does almost everything in this language because Stewart actively suppresses the parametric viewpoint, which is why his Calculus 3 treatment, in my view, is it's easier for the student in some regard because he makes it all formulas, but he's also not really teaching you Calculus 3 because Calculus 3 is inherently parametric. At least this part of the course, it should be. But anyway, it is nevertheless popular to define that to be the integral over c of p dx, and this over here to be the integral of q dy. So in other words, we're defining these integrals here to mean that you parameterize the curve and you simply change your dx to dx dt dt. So what does this all mean? This means a way you can calculate the line integral is to write the parametric equations. So let me just, here's an algorithm for calculation that's, this is an alternative equivalent method. So like number one, write, identify parametric equations for x and for y 2 take differential, to find dx and dy, and 3 integrate. My instructions are slightly vague, all right? So let me put them into practice for this example so that you know what I'm talking about, okay? Yeah? Let's do that. So here, if I'm going to integrate, let's see here, minus, so let me say it this way. So if we have f dot dr along the unit circle again, so I want to integrate along counterclockwise unit circle, okay? Actually, not the unit circle. Let's make it the radius r circle at origin. So first of all, the alternative notation for the line integral is this. You just do like minus y dx plus x dy divided by the square root, in this case, of x squared plus y squared along the curve. You could almost think of it like this. Well, I mean, you can think of it like this. The dr is dx comma dy, and the f is pq. So if you take their dot product, what do you got? You got p dx plus q dy. That's what you're integrating, p dx plus q dy. Now here, what are my parametric equations? We talked about them already, right? X equals r cosine t, y equals r sine t, right? What happens when you take the differential? Well, you got dx is minus r sine t what? dt. And dy is r cosine t dt. And so you literally take these and plug them in to the differentials. And what's the rest of the rules of this game? You plug in the parametric equations into the formula as well. And then you integrate over the given domain. So here this works out to the integral from 0 to 2 pi of like minus r sine t. And what's my dx? Well, my dx was minus r sine t dt. And what's my x? Well, my x here is r cosine t, and my dy was, well, that was r cosine t dt, right? Lovely. What's the square root of x squared plus y squared for the unit circle? Not unit circle, but the circle of radius r.
R.
That's right. It's the square root of r squared, which is, in this case, I'm assuming, of course, you got me. R is positive, right? We're making that assumption. So the square root of r squared is the absolute value of r, which is r, as I was told. And what you got here? So sine squared plus cosine squared. So we have what? We have r, integral from 0 to 2 pi of dt, which is 2 pi r. You could do this same integral, right? Example 4 tilde. If we were integrating, minus y dx plus x dy over x squared plus y squared over the same circle of radius r, what would we get? This notation is pretty nice, isn't it? I will admit, it's a nice notation because it allows you to, make the vector, it allows you to put the formula right there to look at. I mean, but of course you could also put the formula for the vector field here, just the same. I just haven't done that yet. That's another notational option. But here, what is this? We're calculating the line integral of minus y over x squared plus y squared, comma x over x squared plus y squared. The calculation's exactly the same. What's the difference? Yeah, we get an r squared down here instead. The r's cancel, and we, instead of getting 2 pi r, we get 2 pi. Irrespective of radius. The integral around the circle of radius r is 2 pi, independent of the choice of r. That's interesting, isn't it? Well, it will be interesting. That's an interesting example. Maybe the most, well, is it the most interesting example? It's in the running. Let me show you a proof of something before we finish today. So we've been doing some examples today, right? And I've tried to do things outside of the notes so that you have more examples. There are some examples in the notes too. I probably did some of the same examples because I am a creature of habit. But example 7.3.2 I did not do, and that one's pretty ugly. So there's a good ugly example for you to chew on if you want to read it. But here is a calculation that is important that we should talk about, that I'd rather talk about than write out for you guys because, time is limited, even in here. And so the line integral is done with respect to an oriented curve, right? So what happens, but the integral was written in terms of a parameterization of the curve. This begs a question, how do I know that the integral doesn't depend on my choice of parameterization? Right? That would be very embarrassing. If I chose a different parameterization and I got a different answer for the integral, that would be problematic, wouldn't it? So what this calculation shows is that if you reparameterize the curve, right? If you reparameterize the curve, if I swapped out t for basically for u, instead of doing gamma 1 of t, I did gamma 2 of u. Well, when I do that, the chain rule brings out a derivative of the parameterization function, a du dt. But in so doing, we can do a u substitution, and the bounds change as well. So the long and short of it is that the line integral done in one parameterization and the line integral done in another parameterization are equal. However, there's strings attached. It has to be a consistently oriented curve, right? In other words, the u has to be increasing. I have to begin and end at the same, like my starting point and my ending point has to be the same for both parameterizations. Now you can also reverse a curve, right? You can parameterize it in the other way. We talked about that before, right? And if you were to reverse the parameterization of the curve, that would end up flipping these. Like a would go, like they would reverse order and you'd get a minus. And so that's why the integral is sensitive with respect to the orientation of a curve. Very, very important property is this. If we reparameterize the curve in the other direction, if we reverse the curve, then we get a minus integral of what we started. And that's because if you reverse the orientation, we call that minus the curve, okay? So like, for example, for the circle I've been doing today, the counterclockwise circle, if instead I oriented it in the clockwise way, we'd call it minus the curve we started with. So a minus in front of a curve speaks to the orientation. And this is a good notation because if you think about it, if you did like the curve and then minus the curve, you took the unit of both of those, well, you went nowhere, all right? And so like the union of c and minus c in some sense is 0. And so this notation also is just really nice, right? Because you see how that works? The integral over the reversal of the curve, which is minus the curve, is minus the integral over the curve. So the notation plays nice together, like the reversal minus, and this is just a literal minus. So anyway. So I thought I should mention that to you. And here's the calculation we did earlier. So that's pretty much it for today. Tomorrow we'll talk about conservative vector fields and what that means and how to calculate it. So, oh, I think I think I also have the calculation in here of the PQR thing. Oh man. Oh, maybe it's later. There it is. So here's the definition of the integral PDX, QDX, RDX. Usually use QDY. Look at that. Good grief. That's a DY. That's a DZ. What idiot wrote these notes? Thanks, guys.